Okay, thank you very much. So manufacturing challenges, Oliver talked about manufacturing challenges of micro-LED for flat panel. The complete opposite in terms of infrastructure and specs is micro-LED for AR. I always like to start with a very technical slide, just saying, what do we actually need for AR? And for AR, okay, Uwe Vogel already said, hey, these are the different optics concepts. But if you want to go for AR, I would say the main concept is still the waveguide concept. And for waveguide, you need a display which is a very high resolution. We talk below 3 micrometer pitch. Otherwise, you don't have a small enough chip. You need crazy brightness levels. 1 to 10 million nits white light. Power consumption for the usual scenario should be actually okay as well. Much below what image quality perfect. So laser scanning is, for example, always a problem with this approach. And then, of course, most important, you need to be able to manufacture it for a reasonable price, similar like a mobile phone system. And all those specs together, you need to achieve for AR. And actually, no existing this big technology can do that. And that's why everything hope is on micro LED. But micro LED for AR, I said already, you need to have 3 micrometer or below. Otherwise, you need at least full HD or larger. The chip is too big and there's zero yield. So 3 micrometer, what options do you have? You can, of course, start with a die-to-wafer transfer. You make a 3.5 wafer in a 4-inch, 6-inch fab. You take the 300 millimeter wafer from the CMOS, and then you do indium bumping. Now, this is done standardly for infrared imager, and it's an established process, but established is as well a good yield. You only get up to 8 micrometer, maybe 7 micrometer. And if you want to go for space military, you can show a nice demo for 3-4 micrometer, but it's actually not a credible way to go, because it has been done for infrared imagers for 20 years. Why would the micro LED be something very different? So the problem is really actually how to make the integration of the 3.5 with the CMOS. And the only credible integration approach below 8 micrometer is you go to a full wafer monolithic approach. And that means that you basically go either sequential 3D, you put a metal layer on a 3.5 epi wafer, you put a metal layer on a CMOS wafer, bond them together, and then you make basically pixel isolation. That's, for example, like JVD in China is doing it, credible concept. Or, and that's what we think is the way to go, is you go to the standard established wafer-to-wafer hybrid bonding, where you take 2 equal-sized wafers and bond them together with hybrid bonding, dielectric, metal. And that's how you actually produce an imager. Now, we think that's the only credible way to go if you want to have high volume with the right precision and with the right yield. The problem is, of course, first thing is the CMOS is a 300 millimeter wafer. The AP is normally not a 300 millimeter wafer. And you basically need to solve those integration challenges. And that's what we're up to. And then the second challenge, which I always like to talk about, is how to make color. And there are endless concepts of how to make color, but all of them have actually some drawbacks. And I would just like to shortly point out what are some of those drawbacks, because it's always important to know what are the limitations. The drawback, for example, you could make an individual die to laser transfer, similar like Coherent showed about micro LED on flat panel. But now, if you talk about a pixel pitch of 3 micrometer, minimum 6 million LEDs per die, 0 defects pixels are normally in the consumer mobile phone and consumer space required. There's no credible yield possible. You can go to color down conversion. You transfer an AP die onto the CMOS readout and have blue LEDs, and then you make down conversion. But down conversion normally, if you target 1 to 10 million nits, you talk about 5-10 watt per square centimeter blue light. No quantum dot perovskite nanophosphor material can get that right now with a good lifetime. You're an order of magnitude off. Nice concept recently shown is dynamic pixel tuning. You basically different current densities have different wavelengths. But of course, that means for red, you apply maybe 1 amp per square centimeter, for blue, 100 amp per square centimeter. And then you need to balance RGB. And actually, you're limited by the one which is red, which is the lowest brightness. So in the reality, you will not get much above 20-30,000 nits either. So what is left is basically what we take as our first approach, and the same approach is, for example, shown by JVD as well. You use an optical combiner, make 3 separate dies RGB, and then you can do that with a waveguide or a prism combiner together. And then, of course, there's still a lot of other concepts how to stack the AP layer together, stacking them by growth, by bonding, or stacking the complete LEDs. All of them will have impact on the efficiency. Basically, yield will be a much bigger challenge, and efficiency will be a much bigger challenge as, for example, if you just go for the optical combiner technique. And last, to talk about technical specs at the beginning, it's performance. Uwe Vogel already said, hey, a micro LED is unlikely to be more efficient as an OLED. I fully agree with him, because your losses are actually based on optics and not necessarily based on some recombination losses. And optics simply dictates, okay, you want to have 10,000 PPI, that means below 3 micrometer pitch. You know what your internal IQE from the different AP wafers, gallium nitride, InGaP is, and then you know what's the N value of those materials, how the light goes from the materials itself into air. And then you know how much light can couple directly out. And if you want to get more light out, as those here 5 to 9%, then you basically need to actually catch wave-guided light and get it out. Now, if you have a large LED display, let's say an LED 5 micrometer with a pitch 10, 15 micrometer, that's not a problem. You can maybe put sidewall mirrors in, catch wave-guided light, and have given another chance to get the light out. But if you have actually a 1 micrometer AP layer, you have it in a 2-3 micrometer pitch, there's no way that you can get wave-guided light out. And then you still, of course, need to be able to focus light. And there, of course, there's some advantage what you can do with micro LEDs. For micro OLED, you always have a Lambertian emitter, and it's not so easy to make on an OLED a focusing structure. On an LED, you can make a focusing structure, and that's really the benefit. And that's basically all of those three things come about what I want to talk about manufacturing. Why is it important for yield? Now, actually, the reason why we as Micledi, we are a startup 5 years old, and we were founded because we perceived it as a problem to get, how do you make manufacturability in volume? And manufacturing in volume, that means, hey, you can start with an R&D process, make a beautiful demo, and then you can build basically a fab around your beautiful R&D process. But you will spend 100, 200, 300, $500 million, depending on, do you talk about the 4-inch or a 300 millimeter fab, just to build the most simple fab. And you will immediately have a capacity of 50 to 100 million units. And if you want to fill this fab, if you don't fill it to at least 80, 90%, you will lose money. Now, you know that AR market is not yet there. So we say, okay, the only way how you can do it is you simply assume that you can make a process which can run in a standard CMOS foundry, use existing tools, but then of course you need to make the full process flow that it can really work into a standard existing foundry. And that's the concept which Micledi pursues since we spun off from EMEC. And we use really production tools at the pilot line of EMEC to make our developments. And the developments is really about the concept of what can you do with yield. Yield is everything. And basically, Coherent talked about transfer yield. In our case, we talk about really pixel yield. Consumer product, you need zero pixel defect density. So you need to use processes which you know from semiconductor that you can get perfect yield. And perfect yield is, for example, the 3D backside illuminated imager, where you stack basically a diode array on a CMOS wafer with something like 100, 200 nanometer overlay down to 1.5 micrometer pitch in production and 500 nanometer pitch in R&D. So now we need, of course, to replace the 300 millimeter silicon diode wafer with a gallium nitride wafer, which we actually don't have. So how do we create it? We basically take in best-in-class AP wafer, 6-inch, 8-inch, redistribute AP dies on across a silicon wafer, which means every AP die is basically the size of the final display, full HD, for example, 4x6 millimeter. We redistribute the AP, remove it so that there's no only 1 micrometer of AP left, and then we planarize it. And basically, we have now a stress-free silicon wafer with a super thin AP layer, and we can move it through a standard CMOS fab. Use the same process like we make a backside illuminated imager. And that you can actually see here. You can see here how actually a single LED looks like. You see basically the back end metallization, copper metallization of the silicon wafer, bonded to the LED, and then you can see here the emission zone in a 1.52 micrometer large emitter. And you can see here, then you look on the 300mm wafer, you zoom in, and then you can see really a die. And this array is basically the size already corresponding to full HD. But in the first approximation, we actually didn't use a CMOS, we used just a metal silicon wafer with some metal layers to really develop the process and then design the backplane. And with that, we can get a reasonable yield already now, even though we don't use only a pilot line. And the alignment accuracies between the front and back end wafers is easily below 200 nanometer. So, and we can basically process as well wafer level optics on top of that with super high precision. Just an example how it actually looks, if you look at the die, this area here is basically the gallium nitride, and here we have then test patterns, either in blue, green, red, which you can see. And you can, this is, for example, a 1 square millimeter big face of John Lennon, 480 by 320. And you can basically expand it. And even if you expand it by factor 3000, you still have enough light in daylight. So that means you are in a few million nits. And you can put it in glasses. It is now, of course, not video capable yet, but if you take it in a standard commercial waveguide, you actually can see that it's really bright, that you really can work in bright daylight against the sunlight. Now, one thing which I always want to mention if I talk about efficiencies, Jürgen mentioned micro LEDs are not much more than efficient than micro OLEDs, only they can sustain much higher current densities. And I said already, the real efficiency within the apex angle, which is relevant for us, is normally in the range of 1–2% more is theoretically from the optics not possible. But still, people sometimes measure up to 8, 9, 10% at 3 micrometer pixel pitch. How is that actually possible? And the explanation is actually quite simple. If you have an emitter, which is really emitting, you get maybe less than 9% of your light can you directly get out of your pixel. But a lot of the light is wave-guided. And this wave-guided light is then scattered at neighboring pixels. And if you just use, for example, an integrating sphere, photodetector, etc., you will always measure this light. And then you basically will completely overestimate your efficiencies. Now, as an example here, I take a paper by one of our competitors, and that's already one of the best ones. They make a lot of effort to eliminate the wave-guided light. But already from the published curves, you can see that you have something like 3–4% of the light is still in the neighboring pixel coming out. If you integrate it over the full 2D area, you measure immediately that you are here overestimate your light by maybe factor 1.8. So I want to repeat, efficiency is better as, let's say, OLED, you will likely not achieve, but you can achieve much better brightness because you simply can pump in 2–3 orders of magnitude higher current density in. And of course, one question is always, how can you focus more light? The good thing is you're talking about a solid semiconductor system. You can basically process things like Fresnel lenses on top of that with super high precision. Here we make multi-level Fresnel lenses with 20 nanometer alignment accuracy because we use the latest generation of immersion steppers. And then you can basically focus shallow beams, bend them upward, and get more light out. And in addition, you can get a great crosstalk. So where we are now, we basically used our seed funding to prove that we can run this process flow on production tools, and we can really show blue, green, red gun. In parallel, actually, we were working as well as on ALA-INGAP, but there the challenges are more about how to make that CMOS fab compatible. We have now started the process actually to transfer this process to a foundry. But most important, we basically now are in the process of actually making our ASIC design. Advanced node ASIC design takes a while, it's very expensive, but we hope to be out with our product in Q4 of 2025. And that's kind of like a mix out of a scientific story as well as about technology challenges about making the micro LED for AR. And I only want to repeat, the biggest challenge is how to make production ready. And we think the only way how you get the price and the quality point is if you do it on a 300mm processing line, actually in a foundry. And if you look at cost of your display, and I'd say the bill of material should be below, like a mobile phone display. Your AP defectivity determines your final die yield. That means, for example, sapphire, if you grow GaN on sapphire, it has a very high defectivity normally compared to GaN on silicon. This is already a big problem. And finally, about efficiency, actually, the efficiency is limited by optics, so you lose basically all light below the angle of internal reflection. And that's basically what we are contributing to the photonics development in Europe.